We've been all told we should test our software, but what happens when we don't? Sometimes it leads to strange and unexplainable events. Is testing more always the right solution? What do bugs reveal about software? And how can we use those lessons to build more resilient systems? Let's talk about the most bizarre software bugs in history. It's 2018, the airport in Jakarta wakes up. The sun rises over the horizon, planes are heading to the runway, everything is as usual. Inside one of these planes, two pilots sit in the cockpit. Nothing usual. They've done this ton of times. Together, they've got over 5,000 hours of flying under their belts. They go through the regular pre-flight checks, everything looks fine, instruments are good, weather's great, no issues at all. The plane heads out to the runway. Engines start roaring, it picks up speed, and they're in the air. Everything is smooth. A few minutes later, the pilot reaches for the controls. Something feels off. The nose of the plane suddenly dips. They didn't do that. The captain pulls back on the controls, and the nose lifts. For a moment, everything seems fine. Maybe it was just a turbulence. Nope, it dips again. A warning flashes, airspeed disagree. What does that even mean? They have no idea what's happening there. They check the dashboards, they go through the emergency checklist, but neither of them really know what's going on there. And they're 5,000 feet in the air. They try to pull the nose again, but the plane is pushing back. It feels like as if there was something else or someone else flying the plane. The plane races towards the ground at full speed, and then at 11 p.m. 32 minutes, Lion Air Flight 610 disappears from radar. What were the pilots actually fighting? Was it the turbulence? The engines? Or maybe just a few lines of code they didn't know about? To find out, let's go back to year 2010. As most of you already know, the biggest aircraft manufacturers are Airbus, which is based in Europe, and Boeing, based in the US. And they've been competing for decades. In 2010, Airbus made a big move. They announced the A320neo. You can see it on the right side. It was an updated version of their best-selling plane, A320, which is on the left side. And as you can see here, it has the same design, but it has just bigger and more efficient engines. What that means is that the fuel costs were lower and the operating costs were lower, so airlines loved it. Within months, Airbus received thousands of orders. And Boeing had a problem. Their best-selling plane, the 737, was less efficient and more expensive to fly compared to Airbus. So they had two choices. One, they could build a brand new plane, but that could take for years because it's very hard to design and build a plane from scratch. Or two, they could just modify the existing plane and make it more competitive. So because they were running the market race, they chose the second option. So in 2011, Boeing announced the 737 MAX. The idea was very simple. Just put bigger engines on it, just like Airbus did. But there was one problem with that. If you compare these two planes, you can notice something, and that's that the 737 sits lower to the ground. So that means that you cannot just put bigger engines like Airbus did, and because they would just not fit under the wing. So how can you fix that? So they came up with an idea to move the engines forward so they could fit. However, what happens when you move the engines forward is that you shift plane's balance. Why? Because engines are very heavy. They're one of the heaviest parts of the plane. So if you move the heaviest part forward, the aircraft's center of gravity shifts, making it more likely to tilt. And you can see here on the picture above, you can see where's the center of gravity. And on the second one, you can see that the engine is bigger and it's more towards the left side, so the center of gravity is also shifted. Now, this necessarily isn't a problem. If you're a pilot, you know how to fly a plane that has a tendency to tilt. This is not a problem at all. But there's one catch. If you want to introduce a new plane which behaves differently, you have to train your staff. And training takes months, sometimes even years. And Boeing didn't like it because they were losing the market race. So they came up with a very interesting and a very unique idea. So instead of training pilots, why not add a piece of software that makes the plane behave exactly like the previous version? So they invented the maneuvering characteristics augmentation system. The way it works is that if a plane's nose tilts up, the system corrects it by pushing it down. But there is one catch. Pilots didn't know about it. So if you wonder how it is, imagine you're driving a car, you're going straight, and suddenly your car just drifts left and right, you end up in the opposite lane, and you have no idea what's happening. And that's basically what they did. If you want to see, there is a simulation on YouTube where they put an experienced pilot go through the same conditions, and he described it as, quote unquote, "It's a horrible situation, it's unimaginable." Now, let's take one more step back. How do you actually determine the position of a plane's nose? And this is a very important question because it's related to the software. In aviation, the industry standard is that all sensors measuring critical data, like speed or position, must be duplicated. And if both sensors give the same reading, like you can see here, then it is considered correct and it's displayed to the pilot. However, if two sensors give different results, the pilot is alerted and follows a specific checklist of action to resolve the issue. And for each issue, they have a specific checklist. They just go through it, so it's a standard process. Now, second problem is that this software relied on one sensor. The sensor called angle of attack was used to determine the plane's nose position, and it was just on one side. Why? Well, we don't know. It's not in any official reports, definitely not an industry standard, so the best we can do is guess that it was some sort of a management decision, probably to reduce costs or complexity. So let's put all of these pieces together. What happened with Lion Air Flight 610? Boeing added a piece of software to automatically adjust the plane's position if it tilted up too much. That software relied on a single sensor. That one sensor failed because it was miscalibrated, so it was sending incorrect data to the system. The software got activated unnecessarily and forced the plane's nose down, and the pilots didn't know that the software existed, so they didn't know how to disable it. Now some of you might be wondering, but how is this possible? Like, has this plane ever been tested? So in March 2017, the Boeing 737 MAX received certification from the Federal Aviation Administration, and the official statement said, to earn certification for the 737 MAX 8, Boeing undertook a comprehensive test program that began just over a year ago with 4 airplanes plus ground and laboratory testing. Following a rigorous certification process, the FAA granted Boeing an amended type certificate for the 737 MAX 8, verifying the design complies with required aviation regulations and is safe and reliable. But after the crashes, investigators found something alarming. The plane was tested, but it turns out that the FAA delegated large parts of the certification process to Boeing itself. So that means that Boeing was reviewing its own work. So critical safety systems were never actually evaluated by a third-party authority. It was Boeing engineers who signed it off as safe and reliable. After the crashes, the 737 MAX was grounded worldwide, and in response, they identified 8 critical safety issues that had to be fixed before the plane could fly again, and Boeing was also charged with fraud. So Boeing made several changes to fix the problem that led to the crashes. 2 sensors instead of 1 to mitigate a single point of failure. The software doesn't anymore activate repeatedly. Before this, it worked in a way that it would repeatedly activate, so if you want to lift up the plane, you were not able to because the software was just activating every 5 seconds. The movements are now limited. It just activates once, and the range of the movement is limited. Pilots know that it exists, so there's better pilot training. There are new emergency procedures in case something goes wrong. There is a warning that's always turned on. In the past, there was a warning only if you pay for it. And there are new sensor calibration checks to make sure that if sensors don't work, that pilots know about it. And as you can see, it's never just one thing that causes failure in complex systems. And in risk management, there's a model called the Swiss cheese model. So imagine you have slices of Swiss cheese with holes in them. One hole in itself, it doesn't matter because there's no hole on the next layer. But sometimes you get unlucky and all the holes line up, and that's when the failure happens. So in this case, the software had a flaw, the pilots weren't trained on it, so there was some human error, and also the plane had only one sensor, and that one sensor failed. And all of these by themselves might have not caused a disaster, but all of them together, that's what basically made it deadly. So what does it mean to us? Some of you might be now thinking, well, I'm a Django developer. I don't really, program software in planes, or I don't work on life critical systems where bugs kill people. But this model applies to all complex systems, and you can find it in all major organizations. When there's some big failure, when something happens, it's never just one single thing, but it's always like a chain reaction that multiple things happen at once that led to the disaster. And so why is it so hard to catch this kind of failures? Like some of you might say, but can you just not test all possible outputs? Well, it all comes down to combinatorics. So if you have one input, you have one output. If you have 5 inputs, you have 120 possible outputs. If you have 10 inputs, you have over 3 million possible outputs. And this is all assuming that your system is deterministic. So think about modern software. How many lines of codes are there? How many people work on it? How much of infrastructure is involved there? From writing a piece of code locally to running it on the server, there are 1,000 things that can go wrong. So what can we learn from a case like this one? First, single points of failure are dangerous. In this case, it was obvious they were just using one sensor, and that one sensor failed, sending incorrect data. Failures are often a chain reaction. As you have seen, there were multiple things that happened at once. There were lots of flights with this plane. It was tested, but it was this specific case where multiple things happened. Software should never do something users aren't aware of. In this case, pilots didn't know that there was a software flying the plane they were supposed to be flying, but I think this is applicable for any kind of software. If you write software, don't surprise your users. They should be always aware what it's going, and it should be very predictable for them. We've just talked about how failures, when combined, can lead to a disaster. But sometimes a single mistake is enough to cause worldwide disruption. Imagine this. You're a developer at Google, it's a normal day, and you push a simple update to Google Safe Browsing, the system that warns users about dangerous websites. Just a small change, nothing unusual. And then you realize that every single website on Google is marked as dangerous, including Google itself. That's exactly what happened in 2009 when a Google engineer made one tiny typo. For 40 minutes, every Google search result said, "This site might harm your computer." And even Gmail was affected. The best part of it is there was just one service that was not affected, and that's the ads. If you're wondering why, I have no idea. The ads always work. They're always there to spam you. So what went wrong? One of the engineers was updating the malware registry, which is a list of dangerous websites, and instead of entering a specific URL, they accidentally added just one character, a /, which means everything. So what we can learn from this is that typos happen, and sometimes testing more is the answer. But not every bug needs fixing. Some are so iconic that they never get fixed at all. Who here knows the game Civilization? Oh, lots of people. So it's a strategy game where you build a growth civilization and you're competing against historical leaders like Napoleon, Cleopatra, or Genghis Khan. And then there's Gandhi. He's a leader known for peace and diplomacy. And at first, everything seemed normal. Gandhi preferred negotiations over war, just as you would expect. But as players progressed through the game and civilizations became more advanced, they started noticing something strange. The moment Gandhi unlocked atomic technology, he started dropping nuclear bombs of everyone. So, why? Well, the urban legend says that the developers gave Gandhi the lowest aggression rating possible, a 1. And later in the game, when civilizations became more peaceful, the game automatically lowered aggression scores by 2. So what happened in binary is 1 is 0, 0, 0, 0, 0, 0, 1. Subtracting 2 made it roll to 0, and then to 1, 1, 1, 1, 1, 1, 1, 1, which is 255, the highest aggression level possible. So instead of a peaceful diplomat, Gandhi became the most war-hungry leader in the game. Now, there is one catch, actually. Although it's often cited as a bug, the game designers and developers said that it's not a bug. It started as a joke on Reddit, and it became viral. People loved it so much that designers decided to introduce a bug because it was getting so popular. So in the latter versions, there was Gandhi dropping bombs on everyone, turning a myth into a joke. So what can we learn from this? Well, not all bugs are tragic, and sometimes they become legendary Easter eggs that can even boost popularity. And sometimes a bug doesn't become a feature. Sometimes it just becomes a very expensive mistake, like the one that cost NASA $327 million. It's September 1999. We are at NASA's Jet Propulsion Lab, watching the Mars Climate Orbiter finally reach its destination. Mars Climate Orbiter was a robotic probe, as you can see on this image. It's about the size of a small car, and its job was pretty straightforward. Cruise to Mars and orbit the planet to study Martian weather and climate. Think of it as some sort of a weather satellite for Mars. There were no astronauts on board, no staff. It was just lots of sensors and lots of electronics. The team had been working it for years, and it cost hundreds of millions of dollars to build and launch. So back then, it was pretty much of a big deal for NASA. After 10 months of traveling, the orbiter is finally reaching its destination. It's deployment day, and everyone's been waiting for, and people are watching it on TV. So what was supposed to happen is that the orbiter was supposed to enter the orbit and to come from behind the planet and radio back and say, "Hey, I made it." But instead, there was silence. Minutes pass, hours, nothing. The Mars Climate Orbiter had essentially vanished. So what happened? At first, no one knew. It was supposed to be 110 kilometers from Mars, but then they realized that instead it had dropped to 57 kilometers, so low that it was basically grazing the mountain tops. And at that altitude, the Martian atmosphere tore it apart. It probably burned up or broke into pieces, completely destroyed. But why? What could have pushed it so far off course? The spacecraft was built by an external contractor on the left side, but it was operated by NASA's navigation team, which was a different team. And there was a piece of software that calculated the force of thruster firings, and it was integrated with the navigation software that was reading the data. So one team was generating data, the second one was reading it. And when they checked the numbers were right. But the meaning of those numbers was off by a factor of 4.45. And that's when they realized where the problem was. The first software output those values in pound/seconds, which is imperial measure of impulse, but the navigation software reading the data assumed it was in Newton seconds, which is metric. So over the course of the mission, every time the orbiter's small thrusters fired to adjust its course or orientation, the recorded impulse was misinterpreted. So you might be wondering, how did such a basic error slip through for a mission this important and at NASA? It's a great question. It was mostly, obviously, a communication failure because NASA's navigation team assumed that everything was in metric. And there was a report where it was written that everything is metric, and it was signed by both sides, but probably no one read it, or I don't know. And the worst part of it is that the data had shown inconsistencies weeks before the failure, and some people tried to raise it up, but these weren't fully investigated. It was probably management decision not to investigate it. So what can we learn from this? I think this is actually a great example because even though it's NASA and spacecrafts, so many things are applicable to any kind of software. So first thing is establish clear interfaces. If you have two systems and two systems interact, make sure they agree on formats, units, and overall assumptions. And here we had two systems interacting together and operating under different assumptions, and that's what basically happened. Here it was just one bad assumption that broke the whole system and a huge mission that cost so much of money and time. So sometimes even small mistakes like this one can have huge consequences. Integration tests are useful. If NASA had simulated the orbiter's navigation with the actual data, they might have caught a discrepancy before launch, but they never had any integration tests. And learn and improve processes. After this disaster, NASA standardized units across the organization, enforced stricter checks, and improved inter-team communication protocols. In the mid-90s, a new employee at Sun Microsystems in California kept mysteriously disappearing from the database. People started investigating, only to discover that the issue wasn't the system failure. It was his name. His name was still Steve Null. It turns out that some systems back then didn't still handle the string null properly. I tried to reproduce it in Postgres locally, created a database, inserted the value null as a string, and if I try to retrieve it, as you see, it works fine. But there are bugs like this in various systems, mostly older ones. For example, I found an open issue in Apache Flix. It's an old software that isn't really used anymore, but some time ago, it was an issue in many systems. And we've all heard the urban legend, I have no idea if this is true, about someone who changed their license plate to drop database and attempted a SQL injection attack. And speaking of SQL injection attacks, I cannot not to mention that popular comic, hi, this is your son's school, we are having some computer trouble. Oh dear, did he break something? In a way, did you really name your son Robert Job Table Students? Oh yes, little Bobby Tables, we call him. Well, we've lost this year's students' records. I hope you're happy, and I hope you've learned to sanitize your database inputs. Some automated systems will delete all records that start with test or ABCDE just because they assume it's all test data, even though they're not. If you're now thinking, wait, you said ABCDE? Like, who would give their kid such a name? Well, actually, I have some news for you. Between 1990 and 2020, over 300 babies in the US were named ABCDE. I can only imagine how well this goes with modern software. So, what can we learn from it? Handle edge case in user inputs, because real-world data can surprise you. For a long time, we thought that the most expensive book ever sold was the Codex Leicester, written by Leonardo da Vinci in the 16th century. It was later bought by Bill Gates for $30.8 million in 1994. A book written by Leonardo da Vinci, written by the thoughts of one of history's greatest minds, lots of handwritten pages of scientific observations and ideas that were centuries ahead of their time. So what kind of book would have to be so expensive? Some rare manuscript, some lost work of literature, something of massive historical importance? Well, in 2011, a book appeared on Amazon with a price tag of $23.7 million. And no, it wasn't some ancient text or some rare manuscript, it was a book about the genetic development of flies. And funny enough, just like the bug on the cover, the price was a bug too. So here's what happened. On Amazon, you have lots of sellers who can set their own prices. And they have automatic pricing rules that adjust their prices based on competitors. So one seller set their rule to something like always be 0.07% cheaper than the next lowest price, and the next one had something like always be 27% more expensive than the lowest option. Normally, this works fine if you have lots of sellers, somehow the prices will balance themselves. But here, the catch was that there were only 2 sellers, and their pricing algorithms got stuck in a loop. So every time the system updated, one seller's price went up, and the other one followed even higher. And again, until the book was listed for $23.7 million. As soon as people noticed, the system was fixed, and the price dropped back to normal. So what can we learn from it? Well, be careful about your assumptions. Our field can sometimes seem mysterious to outsiders. When WhatsApp set the maximum number of people in a group chat to 256, the Independent reported it with a comment. It's not clear why WhatsApp settled on such an oddly specific number. That comment quickly disappeared, and it was replaced with a footnote. A previous version of this article said it was not clear why WhatsApp settled on the oddly specific number. A number of readers have since noted that 256 is one of the most important numbers in computing, since it refers to the number of variations that can be represented by 8 switches that have 2 positions, 8 bits or a byte. This has now been changed, thanks for the tweets, DB. Speaking of 256, did you know that trains in Switzerland are not allowed to have 256 axles? To keep track of trains on the Swiss rail network, detectors are placed along the rails. These simple detectors activate when a wheel passes over them and count the number of wheels in order to provide basic information about the plane. Unfortunately, these detectors store the axle count in an 8-bit binary number, so when the count reaches 1111111, adding it 1 rolls over to 888000000, which means that the count is reset back to 0 and the train becomes invisible. So it's a phantom train moving through the network undetected. And if you check Swiss railway regulations, you will find section 3.7.4, which states to avoid falsely signaling a section of track as clear by resetting the axle count to 0, and thus to avoid collisions, the total number of axles in a train must not equal 256. Some 256 related errors are harmless. Some are funny, and some are deadly. The Therac 25 was a medical radiation machine used to treat cancer. It had 2 modes, a low power beam for regular treatment, which you can see on the left side, and a high power beam that had to pass through a metal target to turn into X-rays. The high power beam was super dangerous if fired directly at the patient, so the machine had a safety check and relied on software to make sure the metal target was in place before use. Funny though, the variable tracking the state of the check was called class 3. And if class 3 was 0, that meant that the check was run, the target is in place, and the beam can be fired. But there was one problem. As you can guess, the variable was stored as an 8-bit number, so meaning every 256 cycles, it rolled over back to 0, even if the safety check never ran. And one day, that's exactly what happened. In 1987, in the Yakima Memorial Hospital in Washington, a patient was supposed to receive 86 rats of radiation. But at the exact moment the operator hit the button, the variable class 3 had rolled over from 256 to 0. The machine skipped the safety check and fired the high power beam straight at them. So instead of 86 rats, they got a deadly dose of 8,000 rats. A simple 256 rollover bug turned a life-saving machine into a deadly one. Sometimes it's hard to understand what is a bug and what is a feature. Take Excel, for example. Everybody uses it, even biologists. In 2016, researchers in Melbourne analyzed 18 genome research journals and found that 19.6% of gene studies contained errors. How is that possible? Well, did you know that there are genes called March5 or SEP15? Well, Excel didn't, so it auto-corrected them to a date. So, if 1 in 5 gene research papers had Excel-induced errors, how bad it is in the business world? For that, we turn to the European Spreadsheet Risks Interest Group. It's an organization that studies spreadsheet mistakes. And they estimate that around 90% of business spreadsheets contain errors. So how did they get that number? It sounds very specific. In 2001, during the Enroll scandal, the US government released 500,000 from the company with spreadsheet attached. So researchers studied these emails as real-world snapshot of how spreadsheets are actually used, and they came up with some very interesting numbers. The average spreadsheet size was around 114 kilobytes. The average spreadsheet had around 6,000 non-empty cells. One spreadsheet had 174 worksheets. 6.6 thousand spreadsheets contain no formulas at all, and 24% of spreadsheets with formulas had at least one error. And sometimes those errors cost lots of money. JP Morgan used spreadsheets to calculate risk. Specifically, there is something called value at risk. It's supposed to answer the question, what's the most money we could lose in a 95% certainty? It's based on historical price movements, volatility, and current portfolio positions. The way it works is that if the value at risk is low, traders are allowed to make bigger risks, but if it's high, then they should play it safe. And one specific value at risk calculation was being done in a series of Excel spreadsheets with numbers manually copied and pasted between them. This was supposed to be a prototype, but what happened is that someone put it into production. So the risk calculation was wrong. And the valuation control team, which is a separate team, and their job was to check if traders marking their portfolios correctly, they were also relying on Excel. And those spreadsheets were also wrong. And at one point it got so wrong that one employee started their own unofficial spreadsheet just to track actual profits and losses. And by the time they caught the mistake, it was too late. JP Morgan later published a report detailing what went wrong. After subtracting the old rate from the new rate, the spreadsheet divided their sum instead of their average. This error muted volatility by a factor of 2, lowered the value at risk. What does it mean is that JP Morgan lost $6 billion because someone added two numbers together instead of averaging them. So the biggest thing we can learn from it is that spreadsheets are code as well, so you should treat them like production software. We've seen how software bugs can cost billions. They can destroy spacecraft and even turn medical devices deadly. But sometimes a bug doesn't wipe out a company or cause a huge disaster. Sometimes it wipes out your entire operating system. Bumblebee was a project designed to enable NVIDIA dual GPU support on Linux laptops, allowing users to offload graphics rendering to the discrete GPU. Everything was working fine until one update in 2011. A user created a GitHub issue with a rather urgent message. Install script does rmrf user for Ubuntu. An extra space at line 351 causes the install script to do an rmrf on the user directory for people installing it Ubuntu. Totally uncool dude. The script deletes everything under user. I just had to reinstall in Linux on my PC to recover. Removing the extra space will fix this. Possibly do it quickly. And the author quickly pushed the fix with a comment message that really summed up the situation. Giant bug, causing user to be deleted. So sorry. And of course, this being open source, the community did not hold back in the comment session. How can you complain about bugs, Mr. Anderson, when you have no operating system? Bleeding edge, really bleeding for someone now. No more lack of disk space now. I didn't like that folder anyway. I'm Bajić. Thank you for your attention. I put together a list of resources if you would like to go through it, and I also put here 2 favorite books about software flaws. One is Humble Pie by Matt Parker. He's an Australian-British stand-up comedian and programmer and mathematician, and he wrote a great book about lots of very bizarre stories. And the second one is The Design of Everyday Things, which is about design in general and how people use things in a way that they were designed. I totally recommend. So if you're if you're into reading, and if you have any other suggestions for books, I'm always happy to hear them. And that said, now it's time for your questions.
You told lots of stories, but none of them was about yourself or your own experiences. So what's the closest you've been to a bug or an error that could have appeared in a presentation like this?
I knew that this will be the first question. Well, at each job I signed an NDA contract, so I'm not sure if it's a good idea to reply to this question. Yeah, I don't have any such bizarre stories, definitely, but I don't have any stories that I can share publicly. But if anyone else has.
Are you perhaps interested in more bugs? Because I once made a path traversal bug that deleted my colleague's home folder and stuff like that. So are you interested in more stories? Should I come to you later? Or?
Oh, I am. We have 10 minutes, so.
Oh, okay. Yeah, there was also one other bug in an Excel sheet that I found interesting. That was when I imported a CSV with a comma and 3 digits after it, and somehow Excel decided that it was 1,000 point, so it was not the comma point that I expected it to be. And oh yeah, about the units getting wrong. I'm really interested if there's any official Django option to put a unit next to a float field, because I use it in my production that I extend the float field to add this format. The unit value to it.
I think a lot of the bugs you showed were quite entertaining or interesting, but one thing in common is that there was human error involved in all of them at some point. With the rise of AI-generated code, perhaps making its way into production more often, do you have any thoughts on what your talk on interesting bugs might include in 10 years' time?
Yeah, I think that's a really good thought. In 10 minutes, it could be the most bizarre AI-induced software bugs.
Hi, thank you. Great talk. Do you think all of these problems could have been solved with more testing, or is it one of those problems where everyone feels like they've tested it and don't know until these things happen, and it's only in the aftermath that they make the real learnings? Do you have an opinion?
Yeah, so I think it depends. I think that definitely some problems could have been solved with more testing. So for example, the example from NASA where we had 2 softwares that we used in different units, they had no integration test. So obviously if they had some integration tests, they would have known that they're using different Unix. So that's an obvious one. Or the ones from Google, for example, about the malware registry, they also had no tests. So yeah, but I also think that like we are introducing new technologies and systems are getting more complex, and I think that you can never test all possible combinations. Look at, for example, some very complex systems like aircrafts. How many buttons and different things are there? You test some, of course, you test it, but then you have so many variables. You have human errors, you have mechanical errors, weather. That's also a big thing. And especially when we are like introducing new things, you have lots of the unknowns. You don't know about things. So I think that that's part of the progress. That's like you introduce new things, but sometimes just errors happen, and no matter how much you test, you cannot test out everything. And that's actually, it's a funny story. It reminds me of a story about planes. Why planes have square windows? Well, because in the past they started experimenting with making square windows because customers wanted it, because it looks nicer, whatever. But then they realized that the problem is that the planes at the beginning were made of wood. And if it's made of wood, it's not a problem because wood is very resistant and everything. But then if you use metal, and you have a plane with square windows, you have lots of pressure in the corners. So what happened is that those windows would be in the air, and after many hours of flying, they would just break apart. And that's just because it's a new thing. Metal was not used before that. Before that, they used wood. So I think as we are discovering new things, there'll be always like cases like those.
So most of the examples you've shown were basically software bugs, but the Google example seems like it was actually a configuration bug, and those are basically different. Can you comment on testing configurations and how to make those maybe more resilient?
So my question to you is, what is the difference between software and configuration? What do you call software and what do you call configuration? Because for me, it's like configuration, like software is an umbrella for configuration, for lots of programming, different things, or at least in this case, but maybe try to define it more.
Well, configuration is something you do without changing the actual binaries or the code that runs. Or even maybe a similar error to the Google, or there was a BPF, like network configuration change in Facebook a few years ago that brought all their systems down for like a couple of days. So that's what I think of as configuration, like settings that are not affecting.
Yeah, so
code.
the question is, what is the difference between testing the two, or what was? Can you repeat the question, please?
Can you comment on how to make configuration changes more testable and resilient as opposed to code?
Yeah, I think that's a very broad question, so it really depends what kind of configuration change are we talking about. In this case, I know that they didn't have any tests for this particular thing, and afterwards they added tests, but I think this is a very broad question to now reply in one sentence, but if you want, we can talk about it later if you have any specific examples.
Thank you very much.
Thank you.
Mir, thank you so much for your keynote. I thought it was amazing. A couple of times you made cheeky comments about management making cost decisions, but there is a cost trade-off, right? As you scale up the testing, they're not always just being tight-fisted, are they?
Well, everything is a trade-off, so. But this is a hard one because there are lots of decisions to be made, and when everything works, no one sees that like everything works and there was some decision made, but sometimes people make bad decisions and they make trade-offs and then disasters happen.
Thank you.
Thank you.